All right, we're back. We're on page 200, if you can believe it, of math analysis. And I've actually done something a little weird with this. There was not enough space on the notes to actually do any of it. So I did a weird thing where I created 3 pages, all of which claim to be page 200. And so I'm going to be working on that. You're going to have to do this on separate paper. There's no way it's going to fit. And also I didn't upload that new file. So this is how we're doing it. So these are practice, what you're supposed to be, so if you look at the name, it's a solo problem set. So you're really supposed to be doing it on your own. But I thought if you're gonna have questions, instead of answering the same question a million times, I thought I would answer it once, and then you can watch them and see how I chose to do it. We can certainly talk about them anyway though, but let's see. 2 sets of parametric equations for each of the following. All right, well, I'm gonna do the lame thing first, for sure. I'm gonna say that x is t because y is a function of t, of x rather. So x equals t makes sense. 3/5. That's done. Second set, I don't know, let's go the other way. How about we do like 5 minus t for some reason? No really good reason for that. No even sort of good reason. I just, we need it too. So there we go. That's that. Nothing exciting. Demonstrate an understanding of how these work. Oh, well, I mean, I guess we could have done, so here we go. This is why the videos are all 1,000 years long. I don't know. So if x is equal to 0, y is equal to 2. And then we could say that delta x is 5 and delta y is 3. That's a good one. I like that one. All right, some equations for this. Well, obviously, in the absence of any other directions, we're going to go with cosine and sine. And then what does that one do? That's like, gosh, t equals 0, right? It goes that way. Maybe we could do, I don't know. I want to start here, right? So x needs to start I'm going to start here and I'm going to go clockwise. So x needs to start in the middle and then decrease. So that's going to be negative sine. And then y needs to start at a minimum. So that's negative cosine. Good. Okay. Well, I mean, it's going to start here and go that way. All right. Let's see what the next question has for us. Particles A and B move according to the parametric equations given below. All right, so they're both moving on lines. That's good. Find the time at which their x coordinates, so just their x coordinates. Now, maybe at that time their y coordinates are also equal. We don't really know. It doesn't really matter. We're trying to find the time at which their x coordinates are equal. So that's actually like a weird concept. And when you get to 3 dimensions, it like matters even more. But like, suppose what? You could have one line doing this and one line doing this, and their paths cross and whatever. Like there could be a time, we could find the time at which their x coordinates are equal, right? So their x's are equal. Let's say that this happens at let's say this happens at like t equals 5, right? So at t equals 5, their x coordinates are equal, but their y coordinates aren't equal. And then maybe there's like a t equals, maybe there's like t equals 10, right? Say this happens at t equals 10. Their y coordinates are equal, but their x coordinates aren't equal. So that just means they definitely don't intersect, because at the only time, they don't crash, because the only time when their x coordinates are equal, their y's aren't equal. The only time when their y's are equal, their x's aren't equal. So there's no way their x's and y's are equal at the same time. That's like a weird, twisted way of thinking about the problem, I think, which is, I think, what this problem is making us do. So I'm actually just going to say, like, x of A should equal x of B. So this will give me 2 plus 3t equals 5 minus t. 4t is 3, so t is 3/4. So that's the time at which their x's are equal. So let's update this and say this is at 3/4. Let's find the time at which their y's are equal. So if the time at which their y's are equal is also 3/4, then like they actually collide. And I don't know, and they collide. There's nothing really more to say about that. So this will be y equals, well, I mean, I guess that means, no, there's really nothing more. It's like I want there to be something deeper about that, but okay. I mean, maybe it's an emergency because they collided. Negative, what are you? You're supposed to be an 8. Negative 8t equals 4, so t equals negative 1/2. Okay, so those are the times at which their x's and y's are equal to each other. Not the same time, so they definitely don't collide. In the next part, we're going to, so on the given interval for t, the plane curves traced out by these parametric equations intersect. Find the point of intersection of the paths, the times at which the particles pass through that point. So this is the thing that we typically do, right? They're on different line segments, and so, or different lines in this case, because they go forever. So we're just going to do our system, right? So we have a system. It's going to be xa of, I'm going to say t1 equals xb of t2, and then ya of t1 equals yb of t2. We'll solve that for t1 and t2. Then when we know t1 and t2, we'll plug those into, t1. So maybe I mean, I should always be more explicit than I am. T1 time a its intersection point. And then t2 is going to be the time b is at the intersection point. Okay, I'm going to use a calculator. So I'm going to switch over to the calculator. I'm going to define these on a graph page, and then I'm going to solve this system on a calculator page. So let's see if we can do that. Here we go. So it's like all review stuff, right? And that's the idea, because we basically know, you know pretty much everything you need now to like do problems with parametrics. What I think you should do, though, is try to broaden the depth of your knowledge, like do more things, try to make more things happen. Like it takes like an independent learning mindset to really like do that, but I think it's worth it. And I mean, I would encourage you to do that. Can't really make you. I don't know how to make someone do something. So let's see. I'm going to go to, well, I think this already was a calculator page. Let's press var and just make sure. Yeah, okay. So I'm going to check my first answers. So I'm going to solve x1 of t equals x2 of t for t. So 3/4. At t equals 3/4. So if I do x1 of t, comma, y1 of t, such that t equals 3/4. So 17/4 and 1/4. And then if I do x2 and y2, I get 17/4 and 41/4. So their x coordinates are the same at that time. Then what we wanted to do was the y coordinates. So it's like if they were in a race and they were just racing to get to 17/4, it would have been a tie. Well, would it have been a tie, or they go in the same direction? They're going in opposite direction, so that doesn't really make any sense. Well, no, I mean, I guess you could still be racing to, I don't know. It's like one of those things where everybody like a dodgeball type thing where you start on opposite sides, and then hold on. Okay, that's what I want to do. The scenario that I'm imagining is like, you start on opposite sides of the gym, and then the ball's in the middle, and it's like somebody blows a whistle and you run toward it. They both get to the ball at the same time. And then here, if we do this, if they were racing to 13/2, for y, they would have tied. But their x's are different, but it doesn't really matter because they'd both get to y at the same time. Okay, and then the next thing we wanted to do is like, all right, there is an intersection point. What about that? When do they get to that? So for this one, I'm going to do a system. So menu 3,7, and then system of equations, two unknowns. I'm going to say t1 and t2. And so it's going to be x1 of t1 equals x2 of t2. y1 of t1. So t1 and t2 are called dummy variables because like they both represent really just time, like time in total. but they'll be different because we can't use time both times because we already know that we would not get a solution. So 13/4 and negative 27/4. So T1 is 13/4. T2 is negative 27/4. Okay. And then let's just change this to 13/4. And let's just, you don't need to do both. I just do both. I don't know. It's like the calculator's not going to screw up, but I always check it anyway. Intersection point. I'll go back and show you what I'm writing here. 47/4, negative 49/4. Back to the notes. Let's see. So, whoa. I just scrolled like a ton. Okay, so I wrote down those solutions, and then what I want to do is, like you want to write a sentence. So I'm gonna write a sentence. I don't even know what these are. Objects, particles. So the intersection point is 47/4, negative 49/4. Particle A is at the intersection when T equals 13/4. Particle B is at the intersection when T equals negative 27/4. Okay, so I'm gonna stop the video here, come back in the next one and do more of this, but good problems. I mean, they're a little different, I guess. I don't know, but just practice. So see you in the next one. We'll keep going. Yeah, see you there.